Let's discuss a term called atom economy or atom efficiency. The concept of the atom economy or atom efficiency was proposed by B.M. Trost. Actually, this looks for how much the reactant in a reaction is converted into the final desired product. നമ്മളവിടെ ബൈ പ്രൊഡക്റ്റിനെ കുറിച്ചോ അല്ലെങ്കിൽ വേറെ അതിനെ കുറിച്ചോ നമ്മൾ അതൊന്നും കൺസിഡർ ചെയ്യുന്നില്ല. വേസ്റ്റ് പ്രൊഡക്റ്റോ ഒന്നും എടുക്കരുത്. അതായത് നമ്മൾ എടുക്കുന്ന റിയാക്റ്റൻസ് എത്രത്തോളം മാക്സിമം നമ്മൾ ഉദ്ദേശിക്കുന്ന പ്രൊഡക്റ്റായി മാറിയിട്ടുണ്ട്. So it is expressed usually in percentage atom economy or percentage atom efficiency. So percentage atom economy is equal to relative molecular mass of the desired product divided by total of the relative molecular masses of the reactants. അപ്പോൾ ഡിസൈഡ് പ്രൊഡക്റ്റിൻ്റെ മാത്രം മോളിക്കുലാർ മാസ് എടുക്കുന്നു, പിന്നെ റിയാക്റ്റൻസിൻ്റെ മൊത്തം റിയാക്റ്റൻസിൻ്റെ മോളിക്കുലാർ മാസ് എടുക്കുന്നു. അതിനെ നമ്മൾ ഡിവൈഡ് ചെയ്ത ശേഷം ഇൻറ്റു 100 വിൽ ഗിവ് യു ദ പെർസെൻറ്റേജ് ആറ്റം എക്കണോമി. ഹിയർ ഈസ് ആൻ എക്സാമ്പിൾ. പ്രൊപ്പീൻ ഈസ് ഹൈഡ്രോജനേറ്റഡ് ടു ഗെറ്റ് പ്രൊപ്പെയിൻ. പ്രൊപ്പെയിൻ്റെ മോളാർ മാസം 44ആണ്, പ്രൊപ്പീൻ്റേത് 42, ഹൈഡ്രജൻ്റെ 2. ടോട്ടൽ എടുക്കുമ്പോൾ പെർസെൻറ്റേജ് ആറ്റം എഫിഷ്യൻസി ഈസ് 100%. അപ്പോൾ ഗ്രേറ്റർ ദ ആറ്റം എഫിഷ്യൻസി യു ക്യാൻ സേ ഗ്രേറ്റർ ഈസ് ദ more the synthesis is in a greener manner. Okay. now see, if the atom efficiency is 100%, then you can say there is no byproducts. Now for an addition reaction or a rearrangement reaction, there is no byproducts. There won't be any byproducts usually. So that reaction, the atom efficiency will be 100%. And usually in a green synthesis, green way synthesis, they are suggesting that kind of reaction, addition or rearrangement reaction, rather than substitution or elimination reactions. Now we'll discuss about synthesis of ibuprofen. Actually, ibuprofen is an analgesic. It was first prepared by a British company called Boots. Okay, so the structure of ibuprofen is given in the side. Okay, anyhow, so here we'll discuss the synthesis of ibuprofen so that you will get a much more better idea regarding what is so called the green synthesis. So here actually, yes, Janish, here actually, okay, I can enlarge this much more. See, two different method of synthesis of the ibuprofen is given. In both the synthesis, in the left hand side, on the left hand side, this is the left hand side, here we have what is so called a green synthesis, while this is the classical route followed by Boots company. So this is on the right hand side, it is by Boots company, while this is nothing other than it is by the green method. Now this is a starting compound. The starting compound is nothing other than tertiary, so better than pointer. Okay, pointer is enough. Okay, see, in the starting compound I have, just a minute, you have to wait. This molecule is actually called, see, this molecule, the starting compound is called isobutyl benzene. Isobutyl benzene. So in both the reaction, the starting compound is the same, isobutyl benzene. Now this isobutyl benzene, we'll discuss the green synthesis first, then we'll go to the next one. First it is treated with acetic anhydride. Isobutyl benzene, okay. So So here is a compound called acetic anhydride, and where the catalyst used in the first step is hydrogen fluoride, which is a catalyst. So what happened after the first step? See here, this group has been introduced, and this group is called acyl group or acetyl group. So acylation occurs in the first step. Clear? Treated with acetic anhydride to form, and the acyl group or acetyl group is introduced. Now in the next step is nothing other than hydrogenation. I'll remove each one, otherwise it will be difficult for you. Hydrogenation, that means reduction. You can say simply reduction. So where the catalyst used is Raney nickel. Raney nickel is a catalyst. So what happened during the process? This was a keto group. The keto group is reduced into secondary alcohol, or simply you can say an alcohol group. So that is happened in the second step. Now what is happening in the just a minute. In the final step, see in the final step what happens is, see carbon monoxide, I'm not sure whether this will go away. No. The carbon monoxide is added where palladium is a catalyst. Palladium, Pd, is a catalyst. Now what happened? This OH group is converted into COH group. This is happening during the reaction. I'll repeat. The starting compound is isobutyl benzene. Isobutyl benzene is the starting compound, which is treated with acetic anhydride in the presence of HF as a catalyst, so that acetylation or acylation happens. Then it is undergone in the second step a reduction with Raney nickel as a catalyst, so that the ketone is reduced into what is so called a secondary alcohol. In the third step, carbon monoxide is added where palladium is a catalyst, then secondary alcohol become carboxylic acid. Anyhow, this is the final compound called ibuprofen. Okay, so that's all about the green synthesis, green method of synthesis. So it involved 3 steps and 3 different catalysts: HF, Raney nickel, and carbon monoxide. Remember, during this reaction, acetic acid is going to obtain the byproduct. The only byproduct is acetic acid. Okay. Now I'll remove all these, otherwise the other figure, whenever I am marking, it becomes tedious for you. Okay. Now enlarge this one. Okay, so here again we'll discuss the next one. The starting compound is the same, it is isobutyl benzene, but here instead of HF they use aluminum chloride as a catalyst, the same reaction, while in the second step they use this compound. This is an ester. An ester is used, okay, as the catalyst. Now actually this is called an epoxide formation. An epoxide formation occurs and that undergo a rearrangement actually in the next step. After step 3 there is a rearrangement, and thereby here you got a keto group. Now the keto group is treated with the NH2OH called hydroxylamine, and thereby this group NHOH has been introduced, and which is then treated with the, actually the sodium cyanide it is not shown here, it is treated with the sodium cyanide or HCN, most probably HCN, so that this group will be converted into C double bond N. Then that group, upon hydrolysis, treating with the water hydrolysis, it will be converted into finally COH group. Okay, the same step, the only difference is here in the In the second step, an epoxide is formed, and which is in the third step rearranged into what is so called a keto group. Then hydroxylamine is added. Okay, so these are the steps involved in this reaction. Okay, so what is the difference? This involves only 3 steps, while here there are 6 steps are involved. You can see there are 6 steps during the synthesis of ibuprofen by Boots company. That is a classical route. Now what we can do? Let us have a we'll compare between these two. Listen. So here you have the green synthesis, while here you have the Boots synthesis. See, in green synthesis, you can see acetic acid is the only waste, while in this reaction, all these HCl, ammonia, aluminum, and acetic acid are formed as waste product. And atom economy is higher, 77, and here the atom economy is only 40. That already they calculated. We are not going for that much tedious calculation and all. Now here only 3 steps, so lesser energy is required. 6 steps reaction, heating is required in some steps, so much energy is required. Here the catalysts used are hydrogen fluoride, palladium, and rhino nickel. They can be recovered and reused. Here the catalyst is aluminum trichloride actually. The other reagent, then hydroxylamine, 2-chloroester, and sodium ethoxide. Okay, see, aluminum trichloride is a catalyst here, but you cannot reuse the aluminum trichloride because it get hydrogenated during the reaction. So that's why we cannot reuse it. Okay, aluminum trichloride generally you have to use anhydrous one, and after the reaction here it get hydrated, so you cannot reuse it. The other reagent used hydroxylamine, 2-chlorobutyl ester, and sodium ethoxide, and they are actually not safe. Clear? So we are not using safer chemicals there. So this is the comparison between the green synthesis and Boots synthesis. Okay, so anyhow, the green method is far better. Okay, so that's why they are asking whenever and wherever it is possible. So you go for what is so called the green synthesis. Okay, thank you.